Thank you, Riku. So my work looks at interfaces, user interfaces. And it's somewhat of a paradox because we use them all the time. And they become the primary means for accessing the internet, doing our work, being entertained, socializing with other people. Nevertheless, we don't really want to use the interface, right? It's something that is in between you and the things that you really want to get done with computing and networks. And we all have stories to tell, how critical it is to get the design right. When an interface is poorly designed, we can't find the things that we're looking for, or they're not there, or we're confused, or it just takes ages to do the things that we want to do. But there's an even more serious side to this. Consider driver distraction caused by smartphones, or this infusion pump that you see here, that has a high probability of errors in medication given to patients. On the positive side, interfaces and user experience are playing a major role in many, if not most, innovative disruptions. Consider things like self-driving cars, AR, or VR. They all succeed or fail with interfaces. So for these reasons, it's necessary that we develop methods that allow us to produce reliably good results in design. And the starting point of our work is that we're not really there yet. If you consider the practice and profession of interaction design, it's something of an outlier in the business of ICT for being more akin to a craft than engineering discipline. The designers, they collect data on users, they examine the data, they sketch interfaces like the one that you see here, they prototype them, they take them into field, they get feedback. But at the end of the day, their practice is more based on experience, iteration, trial and error, and team practices. And it's far away from those ideals that we attribute to ICT, like predicting and proving good outcomes. So since 2011, when I started at Max Planck, I started asking this one question. How might we design user interfaces using modern computational and engineering methods? If you go far in that path, then you ask a question like, what would the Watson of user interface design look like? But can we even do that, given that the profession and practice of interaction design is very complex, is very ambiguous, and there's no obvious way of using computational methods out of the box. And indeed, all applications of computational methods, they rely on two principles, decomposition and abstraction. So the first question that we should be asking is, what are those decompositions and abstractions like in the area of interface design? And one important observation that I've been making during these years is that many design problems are combinatorial by nature. So you consider the design of this interface, for example. You have to choose the widget type, you have to select the items that you want to show, you need to order them, you need to label them, you need to give them icons, you need to group them. And many of them are combinatorial. This means that to design an interface insists that you find a good combination of those decisions, atomic decisions. And this is a very valuable observation, as I'm going to show you later, because it allows us to formally define problems and analyze them and even solve them. That's the first step towards algorithmic design. So here's how it looks like in practice. So this is one of the classic problems from 1977. It's the typewriter design problem. And you have an alphabet, letters, and you need to assign them on key grids. And you have n letters and n buttons. And this was one of the first one that was formulated mathematically, and that exposed the size of this problem. So you can think about the number of permutations that you can have when you place letters on this keyboard. And it's n factorial, and it's in the order of 10 to the power of 26. And it's already a relatively large problem. But it's nothing that it would be out of reach for computers, but it's definitely something that is out of reach for humans. And that explains why we have issues with the QWERTY keyboard that we have here, because it was designed by humans. But what I just told you only describes the number of possible designs. It doesn't tell what constitutes a good design. So the computer cannot solve yet this problem. So the second problem here in this space is the definition of meaningful objective functions. In the case of keyboards, what you want to do is you want to maximize typing speed. If you want to decompose that, that means that each individual key press is as fast as possible. And key press means that you move the finger from one button slot to another one. And one of the first insights made in this space in the 1990s was that we can take a law from motor control. It was called Fitts law, and it's a very simple law, and already equips the computer with an idea on, what is a fast key press and what is not. And basically, the business of keyboard design now is about assigning letters, such as to minimize finger movement time, while considering the probability of letter transitions in the given language that you're looking at. So the benefit of this approach is that when you formulate your design problem like this, then you can start using optimization methods to solve them. So they can go through millions and millions of designs in a clever way. Here's an intuition of how one of them works. So in this classic work, this was done 2001. They threw letters on this canvas, and then they took one letter at a time randomly and then move it to some other place. And then they asked from this objective function that I showed, well, is this a good design or not? Can people type fast or not? However, this clever algorithm controls when it explores the design space and when it focuses on designs that it found already to be good. And the outcome that they got using this method is shown here. It's called the Metropoly keyboard. It was optimized for PDAs and stylus tapping. And it has the space in the middle, which is the most common character in English. And then the vowels are in a triangular shape around it. And they tested this out, and they found that this is indeed a faster way to type than the regular QWERTY layout that we have. So everybody got excited about this approach, and there were lots of papers on keyboard optimization. However, they bumped into a major limitation, which was that which was become to stall progress in this field for a decade. It was not clear, and this is understandable because these were computer scientists working on these problems, how to encode knowledge about the human in these objective functions. And that's exactly what I try to address in my own work. It's called model-based interface optimization. And the idea is that instead of a designer generating and evaluating designs manually, the designer defines a task for an optimizer that then goes through millions and millions of designs, and always consulting models that are able to predict somehow how good the interface is for a particular task. And these models come from psychology, cognitive sciences, biomechanics, whatever science that is able to give you predictive models that are relevant for your task. We also work with computer scientists to try to define these design problems in such a way that we can find link to computer science and known problems there, so that we understand something about the properties of these problems and we can benefit from the methods that they develop there. And of course, we work with designers to understand how to make this whole approach compatible with their practices and tools. This is an overview of what we do. So at the core of it all is predictive model. It's pretty difficult to create these predictive models because they should be able to take any instance in these very big design spaces and then say something meaningful and valid about how people will respond or experience or use an interface. And what we've been doing is we've been trying to collect very rudimentary aspects of interaction, dealing with perception and attention and learning and motor control and so on, and formulate them either mathematically or using simulations. And now we can equip the optimizer with an objective function like this. This is an example of one mathematical model that we developed for menu selection. In the menu selection, you're choosing one item from a menu, and this model gives you time that it takes to select an item given amount of experience that you have with a particular menu. More generally, we use a number of models and simulations that deal with these basic aspects that I listed, like reaction processes, choices, strategies, attention, perception, eye-hand coordination. All of them are relevant in interaction. But it's important to note that the code is the computer code is the most flexible known medium for expressing and encoding any knowledge, be that a theory or a model or simulation, or be that an intuition that a designer might have. Right? We will find a way to express that for the objective function. So now putting all of these three things together, what we have a design space, which is here denoted by these two variables, variable A and B. Then you have an objective function that is basically giving a structure to this landscape. And those objective functions, they come from psychology, and they are determining what is a good design in that design space. So if you're maximizing this objective function in this case, you would be looking for the highest peaks in that landscape. And what's valuable here is that for the first time we have a rigorous definition of what optimal design means. But it doesn't stop at finding the one best optimal design. We can use this as a flexible and powerful toolbox for solving problems in design. We can ask questions like, what if I'm allowed to change only one thing in the interface or two things? What would give me the maximum gain? Or if I have several user groups or tasks that are contradictory, then what would be the best compromise design among them? Okay, so to summarize this part, this is a principled alternative to the present paradigm where design problems are defined and solved as optimization problems. Now, that's nice, promising, but then does it actually work? And I'm going to give you an overview of some achievements over the 6 years. And of course, I have to start with keyboards because it's the only classic problems in this area. We've been working on defining this problem using integer programming and finding relaxations that allow solving larger and larger instances more and more efficiently. We got to a point that we can actually solve realistic cases. So we're working with the French standardization organization to do a new mapping of special characters in French language to their keyboard layout. And this is a really hard problem. We have a problem that is in the order of 10 to the power of 179. And we can have pretty good results already in this space. And if everything goes well, this will be the new layout in France. Of course, we want to go beyond keyboards. One of the things that we look at is menus, obviously. I showed that already. And one of the things that we learned first was that you can use the same formalism called assignment problem to solve menu problems that you use for keyboards. And we did exactly that, and we found that you can have pretty good results. You just need to extend the objective function, not to consider only performance, but also things like consistency and coherence. So here you can see one result that we got for so-called Firefox menu design problem, where the input is just a log file coming from Mozilla telling how people select items. And this is a menu that we produce in 3 minutes for that problem. So basically, you don't have to do anything as a designer. You give a log file, and you get out a sort of good starting point for your design. In the application menu design problem, we are also interested in how to color elements and how to size them. So on the right side, you can see an optimized layout. It actually has 3 pages of 75 applications altogether. And on the left side, you see the baseline, which is Microsoft designed Windows Phone app menu. And we used, again, perceptual models, attention models, motor control models. And we optimized this one that we then tested with users. And they found that it's faster to use, and it had some aesthetic qualities that they preferred as well. We started working on the problem web page design, but this problem became quite exceedingly hard. Already with 8 elements, we're in the space of 10 to the power of 81 layouts. And our optimizers were at that point, 2 years ago, not able to solve this. This is one hand-picked result for a small problem. With Niraj, who's actually sitting there in the audience, we're looking at new ways of formulating this problem using integer programming that will allow us eventually to work with realistic problems of 50 to 100 elements, I hope. Here's an example of a visualization that is enhanced using our optimizer. What it does, it basically models how people perceive brightness, contrast, and unit formation. And then that's encoded in the objective function that then decides how to change the transparency of these markers, the size of the markers, and the aspect ratio in order to expose more of the structure of the underlying data set. This can be done, again, automatically. And here's a cool thing. You can use these models also reversely. So I've been this far talking about maximizing people's performance. Well, you can also try to get them fail as much as you want. So you can use this inversely for game level design. Here's an example in this annoying game called Flappy Berg. We produced a version where we can control how often gamers die using these models that we have. Similarly, we can use models of how network users perceive the quality of network service, for example, when they're browsing, and use these models to decide how to allocate network capacity, such as no capacity is needlessly wasted for increases that users will not appreciate or even notice. We can also try to solve some previously unsolved problems, really hard problems. And this is an example of such a problem. The problem is, how do you communicate with a computer vision sensor like leap motion? What is the maximum you can reach as a human, and what would be the gesture set designed to allow that? So we can obtain constructive estimates of the maximum achieved in these interaction tasks. So we used, again, models of hand performance, anatomy, motor learning, and in this particular case, this is just one of the applications. We estimated that we can achieve like 50 to 60 words per minute using this optimized gesture set that we produced. So this is a text entry task. Okay, so thus far I've been talking about optimization for the masses, but if you followed, you notice that all the objective functions that we use, they are not coming from black box machine learning. They are white box models that come from theory and literature. And this allows us to meaningfully calibrate these models for any target population. And we call this ability-based optimization. So what you see here is an example of the regular Android keyboard. And some patients, like patients that have tremor, have big difficulties in using this. And the question is, how should you choose display size, advanced features like word completion, the layout, and so on. And that's what we do with the optimizer. And we found this layout for tremor patients that we're now testing. Finally, we've been shifting our attention also to early stage aspects of interaction design. Those are more conceptual, and those are the kinds of problems that have been typically attributed to the domain of human creativity. And for example, we formulated the functionality selection problem in service design. So when you design a service application, you have lots of different options on what kind of features and functionality you should include. And we created a tool where you can enumerate those options and rate them as a designer. And then an optimizer will explore the space of possible functionality selections for you, and using integer programming. And it's going to take into account a good trade-off between usability, usefulness, user experience, profitability, and implementation costs. And we implemented this tool and invited professional designers to our lab and asked them to use that and versus create functionality sets on their own. And quite amazingly, they ranked the optimized sets as high or higher than the ones that they designed themselves. Okay, so what have we learned and what's going to happen next? To sum up first, there are two main contributions, a pragmatic one and a more scientific one that we're looking at here. First of all, we're looking at improving interfaces for human use. And moreover, in a way that we can even say that this is the best possible interface for this given problem. Secondly, we're looking at formulating and solving design problems in a new way that at the same time is increasing our understanding of those problems, but also allowing us to use these very powerful methods that we have in optimization research. Of course, you've been seeing examples in gesture design, keyboards, menus, and so on. We want to push this even further, and there are three main frontiers where we work. First of all, we work with computer scientists to define efficient and elegant definitions of design problems. We work with behavioral scientists and cognitive scientists to adopt and develop better models of users. And we work with designers to integrate these methods into their tools and practices. So now going back to the practitioner with whom we started. I gave similar talk to interaction designers last year, and they were, of course, both afraid of this, but also excited about it. And then they asked, well, what does it all mean for our profession? How is it going to change? And I made 4 predictions at that point that I think that are still valid. First, I predicted that there will be groups and organizations that will be systematically able to produce better designs, and they will gain some edge out of this. Even better, they will be able to justify and give guarantees for their results. This is very valuable in business. Secondly, you will see some bulk designs automated. So as a developer, for example, you don't need to worry about interface design at all anymore. All you need to know what you want. You tell that to an optimizer, and optimizer will give you a nice design automatically. Third, some of these optimized interfaces will be released and go to the wild. One example is this keyboard that we're developing for the French people. And it's going to be the critical test whether they are actually better than the human designed ones. And fourthly, and this is also something that we're working on, we're looking at combining this with machine learning in order to do what we call self-optimizing interfaces. What does it mean? It means interfaces that are collecting data about how they're used and then inferring models from that data and then using those models as the basis of optimization to adapt and change the interfaces. So in the future, you will see automatically changing interfaces that are taking care of themselves and nobody has to update them anymore. So that's it. Thank you for having me here in Aalto, and thank you for your attention.